Welcome learners and math lovers in the series of videos on topology. We are looking at the connected spaces. In fact, in the previous videos, we have proved about the continuous image of a connected set is connected. Okay, and also we have proved that some subsets of Rn is connected if and only if R is connected if and only if it is an interval. Okay. Now today we will prove that if we have two topological spaces which are connected, then x cross y is connected in the product topology. And to prove this, we will use the definition of our homomorphism, open images, connected sets, and the previous theorem what we have proved. If the union has a point in common, then the intersection is sorry. If the intersection has a point in common, then the union is connected. Okay, that theorem we are going to use in today's video. So let us talk about the theorem which we are proving today. Theorem. So let us take two spaces, say x and y. So if theorem, if x and y are connected spaces, then x cross y is connected in the product topology. So what data we have is both spaces x and y is connected, and we need to show that x cross y is connected in the product topology. And to prove this, we will use homomorphism. The continuous image of a connected set is connected, and the fact that if you have a connected species and if it has a point in common, then the union of those connected species is connected. Okay, so let us prove this. It may be a slightly lengthy video, but understand the proof. It's very elementary proof. Okay, so to prove this, let us use different color. Let us take a point in x. That x0 belongs to x. Okay, so for side by side, let me draw the coordinate axis. So let's take this x first. We have this x and y axis. Okay, and then let us take a point x in x. So this is our x axis spaces. This is y space. Of course, for general topological spaces, this makes no sense. So let us relate this to our R2, right? X plus y in R2. So let us take a point over here. Say x0. So you have taken x0 in x. Okay. Now let us take all those points which are on the line passing through x0 and which is parallel to y-axis. Okay, so let us first draw that. This is this. I don't know how it will be. Here to top and to understand it's okay. Okay, so if you see here, how we are going to write those lines here. We are taking all those points on the line which passes through x0 and which is parallel to y-axis. So if you see, the x coordinate of all those points is fixed, right? All those points, if you take on this line, x coordinate is fixed and y coordinate varies over y. Okay, in R2, if you imagine this, then this line will be x0 which is fixed and y varies over y. So this entire thing is x0 cross y. And our claim is, claim, or let me use some different color to write our claim. Claim the subspace x naught cross y, if you take this line, all those points on this line, x naught cross y of x cross y is homeomorphic. We have seen the definition of homomorphism and many examples, so you go and check the playlist. You can see all those videos in the playlist named Topology. Okay, so the claim is the subspace x naught cross y of x cross y is homomorphic to y. Right? So we are showing that this line, all those points on this are this space is homomorphic to y. And to show that it's homomorphic, we need to define a function f from either from y to x naught cross y or x naught cross y to y, which is continuous function, which is bijective function, and whose inverse is also a continuous function. Okay, and also we have shown that the equivalent definition that f is bijective, f is continuous, and show that f is either open map or closed map. Ultimately, what we are showing is this line is a connected space. All those points on this are the connected space because y is connected, so this will be connected. This is our aim right now. The next 20 minutes we will spend on to show that this is a connected space. Okay, so let us prove our claim. We will go side by side. Go back to our original color. For that means we are showing that our claim is true, or we are proving the claim. Let us assume a function, or let us define a function f from x naught cross y to y. We can also define a function y or from y to x naught plus y. Okay, so you can make the necessary changes. So define by, let us define this, define by. Now remember, here you have a points in x naught cross y, so the points will be of the form x naught cross some point, and here just a one space y, capital Y. So let us define this by f of x naught cross some point in y, so let us take y naught or y is equals to, let us map these 2 points tuple in y. Of course this y belongs to y, and that same y we map it over here. Okay, so we need to show that this is a bijection, right? So I will leave that as an exercise. Show that this is a bijection. So note that f is bijective. Okay, that means you need to show that it is one function and it is onto function. Secondly, we need to show that f is continuous. So this is our function f. We need to show that f is continuous, means there are equivalent definitions, but right now what we will do is we will take an open set in our codomain y, and we will show that the inverse image of y over here is open in the domain. Okay, so for that let us take a subset v, subset of y be open. We need to show that inverse image of this v will be open in our domain. And what will be inverse image? So this implies, what is inverse image of v? It will be set of all those points in the domain. That will be same as, let us write that set first. Set of all those points, say x naught comma y belonging to x naught cross y, such that f of x naught comma y belongs to v. And precisely this set will be nothing but x naught cross v. Okay, you can check this too, it will be same, and that will be same as x naught cross y. We can check this intersection with x cross v, because this, if you take x naught cross y intersection with x cross v, you will precisely get this. Alright, and then so this set is same as x naught cross y intersection with x cross v, because you are taking, since you are taking intersection of this two, this intersection of x naught and x will be singleton x naught, so this is here, and when you take the intersection of y and v, it will be v. So precisely these two sets are same. Okay, if you want a rigorous proof, you take a point over here and show that that point will be here, and another way you take a point in this line in this space and show that this will be in this set. Okay, that is also left as explicit. Alright, so, and if you see, this is our domain, I mean the space x naught cross v. Of course you are dealing with the subspace topology, and this is a set which is open in x cross y. So you are writing this f inverse of v as x naught cross y, that is a subspace, intersection with some open set in the whole space, that is x is open in x and v is open in y, that implies x cross v will be open in x cross y. So altogether we can conclude that f inverse of v will be open in this space, right? And that is nothing but our domain x naught cross y, and that will show that f is continuous. Okay, so let me put that in words here. Since x cross v is open in x cross y, because x is open in x, v is open in y, that implies x cross v will be open in x cross y. This implies x naught cross v, x naught cross v, that is f inverse of v, then you can write, is open in x naught cross y in the subspace topology, right? Because we are writing x naught cross v as x naught cross y intersection with x cross v, and we proved that this is open or this is open in the whole space x cross y, and this intersection with means this is open, and since this is open implies f inverse of v is open in the space, right? So this implies f inverse of v is open in x naught cross y, and therefore f is continuous function, right? Because we have taken, to prove that f is continuous function, we have taken an open set in our codomain, and we proved that inverse image of that open set is open in our domain. That implies f is a continuous function. Next point, what we need to show, that to claim our claim, we have proved that f is bijective function, we proved that f is continuous function, and then we need to show that f inverse is continuous function. Or also equivalently, we have another definition which says if f is bijective, f is continuous, and if f is open or closed map, then f is a homomorphism. So let us use that definition. We will show that f is an open map. Okay, and to show that f is open map, let us recall that a function is open map, or a map is open map provided if you take any open set in our domain, its image is open in our codomain. In that case, we can say that f is a open map. And equivalently, if you take a closed set in our domain, and if the image of that closed set is closed in our codomain, then the function is called a closed map. Okay, so let us show that this f is the open map. So if we show that, if you manage to show that, then f will be a homomorphism. So third point, let us go on the fresh page. So third point, to show that F is open map, and to show that this F is open map, we will take a open space, open set in our domain. So let us take that x naught cross some W be open in x naught cross y, our domain x naught cross y. So you take an open set in x naught cross y, that will be of the form x naught cross W, where W is open in y. Okay, let us this in the subspace topology in x naught cross y in subspace topology. And if you take the image of that this set, if you take image of this set x naught cross W, and if you see the definition of F, if we see the definition of F, you are taking all those points tuples and you are mapping this point to the this thing. So if you take the image of x naught cross W, it will be same as W. Okay, now remember our aim is to show that this W is open, right? We need to show that x naught, the image of x naught cross W is open in the codomain Y, and equivalently we need to show that W is open in Y. Okay, so let us write 1-2 statements before that. Since this x naught cross W is open in the subspace topology, we will use this if required, otherwise we can cancel this. Topology, there is an open set, this is by definition, open set, say G, a subset of x cross y. Obviously this G will be of the form some subset of x and some subset of y and cross product. Okay, such that G intersection with x naught plus y is equals to x naught cross W. Okay, because why because this is open in the subspace, so this open set x naught cross W can be written as the space x naught cross y, where this is subset of intersection with some open set in the whole space. So we are taking open set in the whole space, that is x cross y. Now we need to show that W is open in Y. Okay, and to show that this W is open in Y, we the definition says if you take any point in W, there should be exist some open set which contains that point and that contains that W. So let us take a point in W. So let some point say W belongs to capital W. So if W belongs to capital W, this will imply x naught comma W will belongs to x naught cross W, and this x naught cross W is contained inside G, right? Because x naught cross W will be contained inside G. Okay, why this is so? Because x naught cross W is a G intersection some set. That means this x naught cross W will be the subset of G, and that's why we have written this x naught cross W a subset of G. Okay, now since G is open in x cross y, there is basic open set, there is an open set basic open set, say UW based on W cross V suffix W in X plus Y, such that we can write this X naught comma W will be contained inside UW cross VW, which is contained inside G. This is by definition. Since G is open, and if we have point in G, there exists a basic open set which contains this point and which will contain inside G by definition. And if this is the case, this implies this UW is open in X and this X, and V suffix W is open in Y. And if you see this UW cross with VW intersection with X naught cross Y, this will contain inside G intersection X naught cross Y, because this is contained inside G. So when you take the intersection, this entire thing will be contained inside this, and this is nothing but X naught cross W. Okay, where is it? This is here. Here. G intersection X naught cross W is nothing but X naught cross W, and in this case we are writing that this is a subset of X naught cross W. Okay, but remember our aim is to show that this W is open in Y, and we are almost through. So this U suffix W cross V suffix W intersection with X naught cross Y, and if you see this, what is UW cross VW intersection X naught cross Y, this is precisely X naught cross with VW, because when you take the intersection of this, it will be singleton X naught, and this intersection with VW, so this will be X naught cross VW, and this will be contained inside X naught cross W. Okay, hence what we achieved is this VW is contained inside W. Okay, this is from here. Alright, so and also we know that this W is from VW. W belongs to VW, and VW is contained inside W. What we have started is we have taken a point in W and we got some open set in Y. Somewhere we might have written here. We have said that VW is open in Y such that W belongs to VW, which contains at W. What does this mean? This implies this W is open in Y. If W is open in Y, this implies by definition, by theorem, what we have already proved earlier, this implies F is open mapping. Okay, so we have proved that F is bijective, F is continuous, F is open mapping, and hence F is homomorphism. So F is homomorphism from where to where? F is homomorphism from X naught cross Y to Y, right? So since Y is connected, implies this X naught cross Y is also connected. Okay, in fact we can avoid all those kind of things and we can give a simple proof. Let us, since we have written, let us use the same thing. This implies X naught cross with Y is connected as y is connected. Okay, so there is nothing special in this x naught. If you take any point anywhere in x, and if you take a straight line parallel to y-axis which passes through x naught, that line is connected. Okay. And also similar arguments. If you take any line parallel to x-axis, that will be connected. You fix any point in y. Say for example, if you fix a point over here, and if you take a line which passes through this point which is parallel to x-axis, you can show that that line is also connected by using the similar argument. So let us keep this as an exercise also. So, and let me write directly. Similarly, x crossed with small y is connected subset of x cross y for all y in y. So if you take any point in y, then x cross y, what is x cross y? Y is fixed, and your x coordinate varies. So these are the precisely all those points in this line like this. Okay, so this is connected for all y. Now what we will do is we will take the union. We will take the union of, let us draw that line also. Color we will use different color. So this line, I don't know, this line is also connected. Okay, now what we will do is we will take the union of this line and this line, and we will use the previous theorem. So let us take that union first. Okay, now x cross y, small y, x cross this y, this set, union with x naught cross y is connected. Why? Till now what we have proved is this x cross y is connected, x naught cross y is connected, but that does not imply the union of these two connected set is connected. But presently we are saying that this union is connected. Why? This is because if you look at the diagram, we have this orange kind of line and this blue line. This point is a common point. This is connected, this is connected, their intersection is this point. So the intersection is non-empty, that means the union is connected. Okay, that's why we wrote here that this is connected. Okay, connected as as this x naught and y belongs to this. So let us take this as xy. X suffix y is equals to this union. This is connected and this belongs to x suffix y. Let us make another claim. What will be the union of all these lines? Right? That means what will be the union of all those lines which are parallel to x-axis cross with this line. So let me check what we have written there. We have taken xy. So this xy, x capital X suffix y, is precisely this line union with this line. If you change your y, it will be this line along with this line. So if you take the union, so all those parallel lines which are parallel to x-axis, union with this, you will get precisely the whole space. Okay, so let me write another claim. The whole space x cross y is nothing but union y belongs to y x, y. Okay, obviously this union is a subset of x cross y. To show that both are equal, you take a point in x cross y and show that this belongs to the union, and in that case both are open. Sorry, both are equal. Okay, so this I will leave is exercise. Okay, show that both are same. Now we know that this is connected. Why? Now this intersection of this we need to show that intersection of xy is non-empty. Why? Since intersection of y belongs to y, xy will be containing x naught cross y, right? And this x naught cross y is obviously non-empty, and this implies, by using the previous theorem which already proved, if you have not gone through that, please go through that video. This implies the union y belongs to y, xy is connected, because the intersection of all those y's will be non-empty. This implies the union is connected, and hence x cross y is connected. Okay, this was our aim. Our aim was to show that if we have two connected spaces x and y, then the the product as a product topology x cross y is connected in the product topology. And let us briefly recall what we have done. We have proved that this line is homomorphic to y and this is connected. We proved that this line union with this line is connected, and we proved that this union of all those xy's is also connected. And in short, we proved that x cross y is connected. Okay. In the next video, we will take some examples based directly on this theorem that x cross y is connected if x and y are connected. Okay. And then maybe 5-10 minutes video, and then we will go for the next topic, which will be like if A is connected subset of a topological space X, and if you have any subset in between A and closure of A, then A will be a connected subset. Okay, so next video will be very short, maybe 5-6 minutes. So go through that and go for the exams. Till then.